Thank you, Dr. Jain, and all the organizers to have given me this opportunity to share things that I have learned during my research career at Physical Research Laboratory mostly. And before I start the discussion, let me make a comment that today being a very special day, the Teachers' Day, and I pay my respect and gratitude to all the teachers, all those from whom I learned what I seem to know today. So with this, let me begin a short story on solar eclipse. I, of course, have given several lectures on solar eclipse, but today's lecture, I thought of doing it slightly different. And many things I, in fact, myself learned while preparing for this talk. So I will share those things. And nowadays, as Vaibhav mentioned, that I work for this Space Education Research Foundation, which is at Ahmedabad. And this has a website of the foundation. There is also a YouTube channel. It has done lots of program of space science education and popularizing space science in general. So, and today's discussion, what I try to cover, I have summarized here, that I will first describe the type of solar eclipses, which many of you perhaps know. I'll also share some photographs and videos of some eclipses. Then I will talk about a very simple calculation, but very interesting one, which I would like students to especially do after the talk. And then if they have any question, they can always talk to me or send me email or ask question whenever they are. And there has been lots of experiments done during solar eclipses in the past. But one or two of them I will narrate here, and these are most important ones that have happened. At the end, I will also talk about the artificial eclipse. Natural eclipse, you see very rarely, once in a while. Like the total solar eclipse, we are not going to see for a long time in India. But artificial eclipse can be done anytime, and the scientists have achieved that technology. Of course, that is not for public viewing. There you can do this experiment in space, and do lots of studies that were earlier possible only during eclipse, and many more. And there is a ISRO plan of doing so. So I will also talk about that. Before I begin the discussion, let me also make a mention that the ancient human knew about solar eclipse, and there is evidence or there is a belief that during Mahabharat war, of which the date also people have derived, that is 21st December 3931 BC. So almost 5,000 or more years back, this war took place, the biggest war of the human mankind. And in that war, there was a person called Jayadratha. He was to be killed. And for that, the solar eclipse was used. At that time, perhaps solar eclipse was not understandable, was not known to many people as we know today. But probably Krishna knew that. So in the evening, the solar eclipse was to take place. And so sun disappeared totally because it was a total solar eclipse, and then reappear after a few minutes. And that's when the Jayadratha was killed. And the other interesting, that is a historical perspective of not solar eclipse, but lunar eclipse, total lunar eclipse. That Columbus, when he first went to America, the Native Americans and the team of Columbus, they were not going well together. So there was a fight, And because these people came from Portugal, and their ration was limited, that was exhausted, and they were not, the Native Americans were not ready to share with them. So he then had a discussion with them, and because at that time he carried with him the sky chart and the sky calculation, and one person in his country also have told him that there will be total lunar eclipse on such and such date. So a day before that, he had a meeting with the chief of the American natives at that time. And there he said that if you people do not cooperate with us, do not share your resources with us, then the God will be unhappy, and moon will disappear. You will see that tonight. So, and the next day, when the lunar eclipse took place, the moon disappeared totally. Yeah, and so at that time, this person came to Columbus and said that, sorry, please get back the moon to us, and we will share all the resources that were, and we welcome you to be in America. And then, of course, after some time, the moon was to come out anyway. So it came out and things became normal for him. So these are two narratives where the eclipse were used in a very tactical manner. Now, let me first tell you how the total solar eclipse takes place. The first or the most interesting of the total solar eclipse is that the sun totally covers them. Sorry, moon totally covers the sun. This is moon, that black you see here, and this is because moon is covered, so you see the corona all around it. Of course, this is a simulation, not the actual picture, but actually it happens almost like this. The other interesting things that you see during the solar eclipse is the Baily's bead just before the totality and the diamond ring. These are, you see here, the Baily's beads. And then once moon fully covers the sun, then you see this diamond ring, and then the totality takes place. This also disappears, and you start seeing the corona. And do experiments with that. I'll show you some pictures of that as well. The other type of eclipse or solar eclipse are partial, annular, and very, very rarely hybrid solar eclipse. So let us begin with the partial eclipse. In that, moon covers the sun partially and goes away. So this is how we observe partial solar eclipse. The other one is, it is in fact it could have been a total eclipse, but the moon's diameter is slightly less than that of the sun, so it does not cover the sun completely, so it covers it only partially. And very, very rarely you see the situation like this because of the Earth's geometry, that in some part of the world or some places you will see annular eclipse like this, and other places you will see the total eclipse. So that type of eclipses are called hybrid type of solar eclipse. And I, in fact, have taken part in some of the eclipse observations myself. Here is one example of or a picture shown of a eclipse image under a tree. That for viewing solar eclipse, the pinhole cameras are sometimes used. Many people make their own pinhole camera and see partial eclipse or total solar eclipse with pinhole cameras. In the nature, the big trees where there are lots of leaves, the crisscrossing of the leaves make natural pinholes, and in large number. So in this picture that you see here, the eclipsed sun eclipse sun is, you see. And if there is a annular eclipse, then these things become ring, and you can get those ring structures. Very, very beautiful. One of my colleague, in fact, in 2010, there was a annular eclipse which passed our southern part of India, and he was on his vacation, did not go for any basic observations, but was sitting in his house and saw this the ring-like structure under his own tree, and he made a movie. But unfortunately, he lost that movie. Though he showed me, but after that he lost, and I also do not have a copy. Otherwise, I already would have shared that. And now let me show you a movie where this partial eclipse images under a tree. You see that the tree is moving because of the wind, and you can see that it is the structures are changing position and appearing, disappearing. So this is with the annular eclipse, it becomes even more beautiful. Of course, in total solar eclipse, you don't see anything under the tree, because at that time the light, it becomes totally dark. On 16 February 1980, there was a solar eclipse in the southern part of India. And this picture was taken at Hosur camp. And because 1980 was a solar maximum year, so in that the corona, this is the moon covering fully sun behind, and this is what you see, the beautiful corona. And this corona is more or less symmetric. It is there all around the sun. Many times you don't see that. In fact, even in this eclipse also, if you take time sequence of images of corona, they will all be different. And here is another example of total solar eclipse, which also was in the northern part of India, Rajasthan. And this is a picture taken at Neem Ka Thana in Rajasthan on 24th October 1995, which also happened to be the Diwali day. And here you see this bright corona is not symmetric. It is sort of axisymmetric. So corona is different in different eclipse and even at different time. Now I will show you a very special experiment movie, which is called the experiment of shadow bands. In fact, our country has in fact, now it has 3 stations in the Antarctic region, and one of them is called Maitri. At that time, in November of 2003, this was the main working station in Antarctic of Government of India, and their totality was to be passing on the Maitri station. So the director of that institute which runs the Maitri station, and the institute is called National Center for Ocean and Atmospheric Research. The director, Professor P.C. Pandey, at that time, he called for a brainstorming session as to what are the experiments that can be done during this total solar eclipse. But this was a total solar eclipse because in Maitri, or in the Antarctic region, at that station, from 22nd November onward, the sun does not set for about 3 months. So sun makes a sort of a circle. During midnight, it will come at a very low point, and during the day, it will go up and then make a circle. So there will be sunlight throughout. And this totality, on this particular eclipse, was almost when it was midnight at Maitri. So lots of presentations were made, and there I made a presentation that this particular eclipse is not good for many experiments that usually people or the scientists do during total solar eclipses, but a phenomena called shadow bands, which appears before the totality and immediately after the totality of the eclipse, this will be an excellent place to observe that. And then the institute and the government of India sent a team of 4 scientists, of which Dr. S.M. Bhandari from Space Application Center and Dr. S.P. Bagare from Indian Institute of Astrophysics. They both went there and made this beautiful recording of shadow bands. In fact, this is the only record of shadow band exists world over. No one ever have recorded shadow bands because they are very faint and they appear for a very short time before the totality and after the totality. And usually people go to observe eclipses or make observation of solar eclipse at a place when the sun is at highest elevation. But this phenomena get prominence only when sun is at the lowest of its elevation. And Maitri on station on 23rd November 2003 had that opportunity. So let me play this movie for you, and then you will see that this is the screen that was mounted, and the sun is in front of this screen, and the camera will be towards the sun, and this screen will be recorded, and I will show you how the record look like. Here, of course, right now you are not seeing any structure, but when I play this movie, you will start seeing the structure. So you see, these are the bands moving, these ones. So if I stop it anywhere, they are there, but the manifestation to our eye does not take place. But if I move, so you can see. So these white and dark fringes that are moving, these are called shadow bands. So, and these are seen before the totality. So when the shadow bands will gradually end, when like now the camera is moved towards the sun, and this the total solar eclipse you see here beautifully. Let me stop it here again, and you see that this is the land or the ocean there. Of course, it is only ice, and this black portion that you see here is the moon, and behind that is the sun fully covered, and what you see is the corona. And when I move this movie, you will see that the corona is changing as a function of time, and at the end of the total solar eclipse, you will see that there will be a huge diamond ring, which is also was rare to be seen at this eclipse. And after the totality gets over, the camera will be moved back to that screen, and you will see the shadow bands again. Let's see it again. So this is the totality as it happens, and you see the streamers coming out and changing all over. This so there is corona in this also, but this is not seen here because the land here or the ice or the ocean, so you don't see that. Now you will there's a starting of diamond ring which becomes bigger than the sun in this case. So this is the diamond ring that you are seeing, and once the diamond ring gets over, then the camera will be moved back and you will again see the shadow bands. So this is again the shadow band. Now the shadow bands are moving in different direction. And on this screen, you see this, there are 9 dots. These are put at every 10 centimeter. This is to calibrate these fringes and sort of do later calculation about what is the scale size of the irregularities in the Earth's atmosphere at that time. And the reason that the shadow bands were so clear and they were there for so long in this eclipse is that when the sun is at the lower elevation and we see from the Earth, there is a lot of atmosphere, something like about 10 kilometers of atmosphere the sunlight has to pass to reach us. And because the atmosphere has difference in the neutral density, and also the humidity is different at different places, and there is a wind blowing. So that acts as the irregularity in front of the light that comes from the sun. And it's basically the interference pattern of the very thin sort of arc of the sun. And that is why you see these things as the arced features. So that is what you can also say, it is the twinkling of sun, like we see twinkling of star. There's the twinkling of sun during total solar eclipse. But if the sun is at high elevation, then this phenomena does occur. I have seen it in other eclipses, but there you cannot record because it's very short-lived and it's not so strong. But in this Maitri total solar eclipse, it was really great. And I have shown this movie at so many places, and people really get thrilled by this. Now I'll take you to some interesting calculations that people have made, and I would like you to make that. In this picture, the sun is here, and then you have moon here, and because sunlight is coming from this direction, so there will be a shadow of the moon. This is the shadow. This dark shadow is called umbra, and there will be very large region where there will be partial shadow. Partial shadow means some part of the sun will be visible, the other part will not be visible. So that is called penumbra. So the places where this penumbra falls, you will have the partial solar eclipse. And the place where the umbra falls on the earth, there only you will have the totality. And this length of this umbra or the shadow should reach the earth. If this does not reach the earth for some reason, then no eclipse is seen. Though this condition that this is earth, this is moon, and this is sun, this takes place almost every new moon day. Every new moon day, the sun, earth, moon, and sun, they have this geometry. But eclipse does not take place in all those, because the umbra gets formed, penumbra also get formed, but they don't reach the earth because the alignment is not very perfect. So in a year, only twice the situation becomes so that the eclipses take place, and these are usually separated by a period of about 6 months. Like the last solar and lunar eclipse that we saw was in May-June period, and then now the next one will be in November, December. Of course, these will not be visible from India, but they will take place in different places. And this nowadays, because there is a satellite on top, and as has been discussed in the previous talk, that there is a space station where several astronauts remain. There was a opportunity of some astronauts at that time. Total solar eclipse took place, and they took the image of from the space station, the image on the earth of the total solar eclipse, and you see that here. See, so this that you see here is the shadow of the moon falling on the earth, and it's moving, and the space station also is moving. So this is wherever this shadow goes, that's where you will see the total eclipse. And in the other part, wherever that partial penumbra falls, you see the partial solar eclipse. Now let me go to, and this shadow can be the dimension or the radius of the shadow can be calculated by a relatively very simple formula, that the radius of the shadow that we will see on the earth, RU, This is equal to the radius of moon minus this factor, the distance of the moon from the earth, that dm, minus the radius of earth, divided by distance of the sun from the earth. De is the distance of the sun from the earth minus the distance of the moon from the earth, dm, and multiplied by the radius of sun minus the radius of moon. So this, with this simple calculation, you can calculate how much will be the radius of the shadow with on the earth, which is casted by the moon. And in this, most of the parameters are sort of not so much variable, like this R, radius of moon, radius of earth, and the radius of sun, that is Rm, Re, and Rs. These are not very much variable. They are more or less fixed. The variable parameters are De and Dm. Of that, Dm in fact is the most variable, because the orbit of moon around earth is ecliptic. There is about 10% variation in the distance of the moon from the earth at different time. When it is at perigee of its orbit, it is closer, and when it is at apogee, at that time it is very far. And that's when it is at apogee, that's when the annular eclipses take place. So that varies, and there is about 1% variation in the distance between sun and earth. That is De. So that also has a little variability, but you can probably ignore that most of the time. The main variable is the Dm, that is moon earth distance, which varies from say 357,000 kilometer to about 406,000 kilometers. So that is about 10 to 12% variation, and that in fact decides how long the totality will be, because the larger the size of the moon shadow on the earth, the duration of the eclipse will be larger. And that's why some totality can be as much as 6 or 7 minutes, and there are eclipses where it's only 1 or 2 minutes or even less. And the distance, the radius of moon, earth, and sun are given here. So using these numbers and ignoring that the distance between sun and earth varies, you can also get those numbers as well, that variation. But varying this, the Dm, the distance between moon and earth, you can make calculation and see for yourself how this Ru varies from, and it will vary from one eclipse to the other eclipse. Now, let me briefly tell you about the experiment of discovery of helium, element helium, which we know today, which was not known, and in one of the eclipses that was discovered. And the main principle of that can be understood like this, that this is the continuum spectra of the sun, or the chromosphere of the sun. You see all the 7 colors. But if you remove the continuum spectra and look at only the line emission, then this is called the line emission. That here there is a very red line, there is a yellow line, there are 2 greenish line, and then this blue line and all that. So you see this is the emission spectra. And there was a total solar eclipse on 18th August 1868 in Guntur in India. This also happened to be, the eclipse happened to be in India. One French scientist from France came here to take a spectrum of chromosphere during the total solar eclipse, because chromosphere and corona is visible only during total solar eclipse. So he then found that there is a yellow line at 587.49 nanometers. And this line, initially, he and many others thought that it is the sodium line, because it was very close to the sodium line, but very, very intricate and detailed comparison of the helium and sodium spectra revealed that this was not sodium line, but it is helium line. And that comparison is, this is the scale down below, and this is the spectra of sodium, and you see so many lines. These are the yellow lines around close to which this line was seen, but in helium spectra, so there is a slight difference. This is not aligned with that. So, and the line that was observed in the total solar eclipse in the spectrum of the chromosphere was this, and hence this element called helium was discovered. And since it was discovered first in the atmosphere of sun, that is why this name also was given, helium. And the other very important experiment was that of Einstein. Einstein in 1915 proposed a test of his general theory of relativity, which was a very revolutionary theory that he proposed to the scientific community, and not many people were believer of that. And he said that my theory can be tested by 3 experiments. One, that if you observe the precision of Mercury's perihelion, that was predicted on the basis of his theory. He also said that the other way of testing this theory is deflection of light by the sun. And this, in fact, was done, or this experiment of deflection of light by the sun was done actually by Arthur Eddington during a total solar eclipse. And the third test was the gravitational redshift of light. So in fact, all 3 tests were later done, and it was proved that they are right. And so the Einstein theory got established, and these subsequently were given the name as the classical tests of general theory of relativity. And let me show you the principle of this deflection of light by the sun. It is shown here that if this is the sun, and when we see sun, the star actually disappear, but they are all there. So if there is a star here, actually at this position, and the light from the star almost grazes the sun like this and come to an observer here, because of the gravitation, very large mass of the sun, this ray will bend towards the sun, and so it will be here. And if you then project it back or draw it back straight line from the observer, the star will appear at this position. So that becomes the apparent position of the star. And this cannot be done during the daytime. Only when there is moon to cover the sun fully, at that time you can see the apparent position of this star, not the actual position, because the star will appear to be sitting at this place. And this maximum angle that this of deflection of the sunlight by the grazing line of the star to the observer here on the earth can be something like 1.7 arc second. Arc second, like you have arc minute, it is 1/60th of that is 1 arc second. The sun's diameter is about 30 arc minute. So you divide that by 30, that become 1 arc minute, and you divide that by 60, that is 1 arc second. So it's a very, very small deviation, but even at that time, people were able to measure such a deviation in the star's position. And later, the detailed calculation showed that if this is the sun, and these are the dots are here, are the actual position of the sun, the deviation because of the sunlight will make the position at this arrow point. So this is star. If there was a star here, it will appear to be here. This star will appear to be here. And if there is a, so it depends that it will depend largely, the distance will be more if it is closer to the sun, and if it is away from the sun, the deviation will be very small. And at very far distances, there will be almost no effect. And the actual observation revealed during the eclipse of May 29 in 1999, and this in fact eclipse also happened to be a very large, one of the largest duration total solar eclipse. It was for about 6 minutes and 51 seconds, and it's a very exaggerated picture of the star which was observed, and the observed position is here. Its actual position compared with its 6 months position would have been at this point. 6 months before, the same part of the sky will be at midnight, and there you can image all the star very comfortably, and then compare that with this. So this much was the deviation, and this exactly matched the calculation made by, or the predictions made by the Einstein. So and proved that the theory is right. So this was one of the most important experiment that was done during any total solar eclipse. Now I will come to the artificial solar eclipse. The solar eclipses that I have shown, they appear, you can see them maybe twice in a year, or they can be, sometimes there will be one, at least there will be one lunar eclipse and one solar eclipse every 6 months. So we can have, say, minimum of 4 eclipses, 2 solar and 2 lunar, but they can sometimes be 3, or sometimes, so there can be 5 eclipses. There can be sometimes even 6 eclipses, but not more than that. So that is the, but the space scientists, as we have seen lots of development of the satellites and the satellite technology, the rocketry, and the launch vehicles in the past several lectures. There is a, in that, of course, most of the people describe the orbits like low Earth orbiting satellite, medium Earth orbiting satellite, and the geostationary satellite. But there is a location between the sun and the moon, and at which the gravitational force due to Earth and the gravitational force by the moon at that point gets sort of balanced. And that point is called Lagrangian point. The person who discovered or predicted that there is a location like that in the space. So that's why it's called Lagrangian point. And that is about 1.5 AU from the Earth. And the distance between the sun and Earth is 1 AU, 1 astronomical unit. At 0.15 AU, that location is closer to the Earth, but sufficiently far away. So at that point, the gravitational force of the Earth and the gravitational force of the sun gets balanced. So if we put a satellite there, then that satellite will continuously be able to monitor sun and will be able to continuously see the Earth as well and transmit the data. So there has been several satellites and now launched by NASA and ESA, at that location in collaboration. It's a NASA collaboration or Japanese collaboration. And one such thing I will show. And what they do there, because you can in fact cover the sun here also on the ground, on the earth. Simply if you point your say thumb towards the sun, and your thumb will more or less cover the sun completely, and also the moon. So your thumb almost eclipses the sun. But on the earth, if you do that, if you devise a method of eclipsing the sun artificially, because earth has an atmosphere, so there will be a lot of scattered light, because the sunlight gets scattered by the atmosphere, so you still don't see the corona. But if you go that place where the sun is visible to you and there is no atmosphere, and if you cover the sun, like here in that experiment, this is the sun's sphere or the sun's diameter. This is sun here. So this is one sun is covered here, and this plate, in fact, it is double of that. So it covers twice the sun radius area of the space around that sun. So you don't see, and there is no scattering, no atmosphere, so no scattering. So what you see is only solar corona all around it and its beauty. Now, this is a movie. I will play it, and then you can see that the coronal mass ejection taking place. See, like here. See, you see these steamers going out. This large coronal mass ejection. This again steamer and coronal mass ejection. So you see this beautifully by eclipsing the sun in space at that L1 point. And not only that, you can study this kind of coronal mass ejections there, which is very beautiful and interesting. You can also make many more observations of the sun, which are not possible that you can do here on the earth. And this, in fact, to put a satellite at L1 point, first Lagrangian point, there is a plan by ISRO, and that mission is called AIDA or L1 mission. That there will be a satellite by the name Aditya, and that will be placed at L1 mission. And the main objective of this mission is to study corona and chromosphere on continuous basis, because corona and chromosphere you don't see down here on the earth. Photosphere you can see, but in photosphere also there are lots of emission which gets sort of absorbed by the earth atmosphere. X-rays at various wavelengths gets absorbed by the atmosphere and the ionosphere, which is there all around the earth, and ultraviolet gets absorbed. So many of those observations, photospheric observation, and the observation of magnetic field strength of the sun will be carried out by this Aditya mission. And this will have several sort of individual experiments, like there will be a visible emission line coronagraph, where you can see different lines, emission line coming out of corona. There will be ultraviolet imaging. You can take the ultraviolet image of the sun, which we cannot make from the ground. There is a solar wind particle experiment where you can measure the solar wind density and the particle strength and their energy. And you can also make low energy X-ray spectrometer. There will be a low energy X-ray spectrometer to study the lower energy X-rays, which totally gets absorbed when they reach the earth. So, and lots of studies are being done by NASA and ESA in that direction, and our ISRO will do these maybe next year. And there will be a high energy orbiting X-ray spectrometer, where the high energy X-rays coming from other objects also can be monitored by that, and you will be able to record them there and transmit the data to the earth. and there will be a magnetometer which will measure the magnetic field on the sun. So I think this was my last slide. And let me admit that many of the pictures or are part of the movies that I showed in this presentation are taken from websites. I thank them, the contributors of these, very much for these very educational and interesting photographs and movies. I thank you all because it has been a very long day for all the listeners and observers of today's session, but you all have listened the talk patiently. If there are any questions, write down on the chat box, and the organizers will send to me. I will reply those, or you can write these to any of these email IDs that I have written here. So thank you very much.
Thank you.